Hello students, we are here with a new video in which we will discuss the statement and proof of the parallel axis theorem. First we are writing the statement. What the statement says? The theorem is parallel axis theorem. Okay. The theorem says that the rotational inertia of a body about an axis about an axis like any point on the axis is equal to the rotational inertia about a parallel axis. Rotational inertia about a parallel axis through its center of mass plus total mass times square of the distance between two axes. Now, what this statement says, we can write it in some form like suppose this is the this rotation inertia of a body about an axis. This can be any axis is equal to rotation inertia about some parallel axis through its center of mass. Let's say this is center of mass rotation inertia plus total mass, let's represent with M, capital M, time square with the square of the distance between two axes. Let's say distance between two axes is r square. This is the general form of this theorem. Before we start the proof, let's understand the diagram first. For understanding the diagram, we are drawing here the y-axis. Let me draw the very left side. Okay, this is the y-axis which is the one, and here is our x-axis. Okay. Since we are using some parallel axes, we are drawing here two more axes which are parallel to the y-axis. Since the body rotating is is on the y-axis, so these are two additional parallel axes. And here is some point C over here, and okay, here. And here is some line representing some points over there. Let me use some different colors for better understanding. Okay, and now let's say this is the y-axis and this is x-axis and this is the origin O. Here is some point C. What's its coordinates since this is the distance A and this y distance is B. So the coordinates of C are A and B. Let's say here is some point G, which is basically the center of mass of the axis along or through which the body would rotate, and its points from the origin are xi dash, yi dash. And on the same very parallel line, let's suppose here is some different point P having xi and yi as its coordinates. This means that this whole let me draw a line. This whole distance through P and this vertical distance. It's about this is xi, and this vertical line is y. I guess all the things are clear. Yeah, yeah, all the things are clear. Okay, let's say this is some plane S, which to which some parallel plane is S dash, which coordinates are this, and x coordinates are this. Now I have to prove that statement of the theorem. Also, adding one thing more, let's say um, this is this is labeled as CD, this line, and this line is AB, and this is EF, EF. Okay. Now from this diagram, we can say some things which are like this, that from the figure we can see xi is equals to this is xi, and xi is equals to, now this whole distance is equal to the sum of xi dash, let me write here about xi dash first we draw. Basically this distance till t is xi dash, and the y distance of t, this is y dash. So this is xi dash, and this is yi dash. From from the figure, we can see that if we draw some, look, this is the xi distance. Xi distance is the summation of xi dash and a, whereas this yi is the sum of yi dash and b. So from this, we can write here xi dash xi is equals to xi dash plus a, and yi is equals to yi dash plus b. Now, since we know the formula of rotational inertia, it says mr squared. First, let's write some theory before starting the proof. I would only dictate. If you want to write, you can write it on your notebooks. Consider a thin plane lamina. I'm drawing here, so this is some thin plane lamina in the xy plane. This is xy plane, which can be regarded as a collection of many different small masses. So there are suppose M1, M2, M3, many different small. Since it is a rigid body, and we know that rigid body is composed of many different masses. So this consists of many different masses. Let's say each mass is Mi. To calculate the rotation inertia of the lamina about some axis z, which is perpendicular to these both axes, this here outward some axis z, passing through the origin, but it's also passing through the origin, and perpendicular to the plane, and perpendicular to this plane. Let's say I can't draw here in 3D, so there is some z-axis. Consider the particle P at xiyi, this particle we are considering in the lamina, from the origin O and from the center of the mass of C. The coordinate is this, and this here is D, having center of mass of this axis, and from the origin its coordinates are this, and the coordinates of P are this. Okay, now the coordinates of C, which is the point on EF, are A and B. From the figure we have then write these equations. Now we are starting the proof. We know that rotational inertia is equals to I is equals to mr squared, and for the summation for all particles we will write mi, or just write m. Since we are considering the whole body, at the end we can write mi is equals to capital M. Remember that summation mi would be equal to the total mass of the body. Okay. That is the total mass of the body. Okay, and what is this? This is the distance from the origin. Now, if we are considering this p particle, then what is its distance? Its distance is xi in the x-axis and yi in the y-axis. So, adding the sum of both squares of both xi square plus yi square. From this equation, let's say this is 1, this is 2. From equation 1 and 2, remember that this I is along CD. This I is along CD. This rotational inertia, if the body rotates along this axis like this in anti-clockwise direction, then it would be equal to this thing, what we are going to prove. But remember that this I is along this CD. Okay, I'm into xi square. What is the value of xi? From 1, we can put xi dash plus a whole square plus yi dash plus b whole square close the brackets. Same I at CD is equals to m into xi dash square plus 2xi dash into a plus a square plus yi dash square plus 2yi dash into b plus b square. Multiplying m inside m xi dash square plus m 2xi dash a plus 2 oops not 2 plus m a square plus m yi dash square plus m 2yi dash b plus mb square. Now, there are something common. We can take common. Let's take in common from these two first. So it would be m into xi dash square plus yi dash square plus, and the other two things are these one, m into a square plus b square. Now, what about the remaining two terms? These two terms are remaining. What about this? If you look in the diagram where this mass lies, xi dash in a, xi dash is here and a is this distance, means the rotational inertia about this g. We know that if rotational inertia goes in the along the axis in which the center of mass passes, then it's equal to 0. So we are not considering these terms. And what is this xi square plus yi square? Xi square and yi square are the coordinates of g. So m into, we can write it r square generally. These are the coordinates of g plus m into, what is this, a square plus b square. We will we will discuss it. What is this? It will be where this comes. This is the general form of ICM, that is rotational inertia in the center of along the center of mass. Rotational inertia, that is given in the statement through center of mass. The rotational inertia parallel axis through center of mass. So we are done with one part. Now, what is this a square plus b square? From where this comes? If we consider these two first equations, we can see, let me raise on here for some space. Let me draw again. From here, we can see A is equals to x minus xi dash and B is equals to yi minus yi dash. What this shows? This shows the, as we said in the statement was the rotational inertia of a body about an axis, which was this axis, is equal to the rotational inertia about a parallel axis, which is this axis, parallel axis through center of mass plus total mass m, which would be this mass m, times square of the distance between two axes. Now, what is the distance between these two axes? If you consider this this line, we can see that the distance between these two axes is A and B. Now, how do we find these distances? These distances can only be found if we subtract. Now, look. How can this distance be found? This distance can be found if we subtract this from this whole, this almost this distance. From this whole, this distance is subtracted, then we can have this distance. So that is the thing written over here. From this all, that is xi dash is subtracted, and we are left with A, which is the distance between these two axes along which the body is rotating. And also, what is B? B is also the same, the distance between two axes, these two axes from the whole, this. When we subtract this whole, y1 and y dash is subtracted, and we are left with this B distance. So we can write generally this as plus m to the capital M. As I said that mi, basically this was mi for all the particles, so it is changed here into capital M, showing the total mass of the particle into a square plus b square. Now we know that what is a square plus b square? It is the distance between these two axes. So we can write here I of CD is equals to ICM, which is center of mass, rotational inertia about center of mass of AB plus perpendicular distance between the two axes into mass into the perpendicular distance. We can write it a square plus b square, or more generally, we can write it mr square. And this completes the proof.